director of the CSH. It's a great honor to present to you and welcome a very distinguished guest today. Those of you who know me know that I usually memorize the CVs of people and just repeat them in my mind, but in rare occasions like these, the CV is actually too long, so I wrote it down. And so I'm going to go through it. Sorry, Scott, you asked me to be fast, but it's not possible. So Scott Tremaine is the Richard Black Professor at the Institute for Advanced Study in Princeton. For those of you who do not know this place, this was the institute they created for Einstein after he fled Nazi Germany. Einstein himself famously said of the institute when he was asked to join, "Ich bin Feuer und Flamme dafür." Scott Tremaine did his PhD at Princeton under Jerry Oestreicher. He then was a professor at MIT. He left MIT after a few years to be the founding director of the Canadian Institute for Theoretical Astrophysics, otherwise known as CETA. And since a few years ago, he has been the Richard Black Professor, as I said, at IAS. Scott is a member of the National Academy of Sciences, which advises the White House on science, and also the Royal Society in the UK. He is well known for a series of 10 papers written in the 70s and 80s by Goldreich and Tremaine. Some of you in the audience may know these papers. Among other things, these papers essentially invented this migration that many of you are simulating now. And it predicted the presence of shepherd moons in Saturn's F rings. Scott is also known for something called the M-sigma relation in studying black holes, which is a very active topic in galaxy formation. There's also a limit on the mass of neutrinos named after him called the Tremaine gun limit, page 2. And several of the students probably know this book. You probably have suffered, or actually you have worked through it, Galactic Dynamics. This is one of the Bibles of the field. Those of you who have studied astrophysics have done an exercise in this book. This book to date has, for those of you who like numbers, has about 6,000 citations. And for those of you who are into these numbers, Scott has garnered about 32,000 citations in his career with a H index of 76. But suddenly his influence goes beyond these numbers. And finally, there are too many prizes to mention, but I'll mention a few. Scott has won the Tomala Foundation Prize, the Denny Hanneman Prize of the AAS, the Helen Warner Prize of the AAS, and the Rutherford Medal. And last but not least, I myself spent 3 very educational years at the IAS in Princeton, studying with Scott. It's a real pleasure for me that he's here and he can share his knowledge with us. So I would like to welcome Scott to the University of Bern in Switzerland.
Thank you for not using up all my time. I'd like to talk today about a problem that for many centuries has fascinated physicists and mathematicians and even young children, the problem of the stability of the solar system. It's extremely easy to state. You have a point mass which is surrounded by some number of much smaller masses on nearly circular, nearly coplanar orbits, and you just want to know if the configuration is stable over very long times, where by very long times, I mean up to 10 to the 10th orbits or so. This is one of the oldest problems in theoretical physics. The first person to think about it was Newton, and Newton famously said that blind fate could never make all the planets move on nearly circular, nearly coplanar orbits. But the orbits, as he said, aren't quite circular and quite coplanar. They have these small irregularities. Those irregularities could have arisen from the mutual actions, the mutual gravity of the planets on one another, and would be apt to increase until the system wants a reformation. So Newton's view was that the solar system was unstable and that God had to intervene. God had a service contract with the solar system and had to intervene from time to time to damp out the eccentricities and inclinations and make everything okay again. The other opinion on this was Leibniz, who of course had other issues with Newton. And Leibniz said that Newton and his followers have an odd opinion concerning the work of God. According to their doctrine, God has to wind up his watch from time to time, since otherwise it would stop moving. And he had not, it seemed, sufficient foresight to make it a perpetual motion. So, as in many other things, Newton and Leibniz disagreed. These are kind of encapsulate the doctrines of theism, in which the creator starts the world up and continues to intervene, and deism, in which the creator sets the world up and then lets it run on its own. The problem of stability of the solar system also, of course, has other implications in philosophy. You'll remember from your philosophy courses that Laplace articulated the idea that, inspired by the solar system, that if you had an intelligence that knew at a given time all of the forces in nature and the initial conditions, then the intelligence would be able to predict the future, predict the past, and would understand everything about the evolution of the universe. And this was, again, the capsule statement of causal determinism, which has survived to the present time as an interesting subject in philosophy. The problem's interesting also because you'd like to know the fate of the Earth. There are basically four possible choices. In about 7 gigayears, the sun will turn into a red giant star. It will expand outwards almost to the radius of the Earth. So it will at least heat the Earth to several thousand degrees Kelvin and perhaps even swallow it. Alternatively, before then, it might be that the Earth or the orbit of some other planet is unstable and the two collide. Or it could be that the Earth's orbit is unstable and it falls into the sun, or it could be ejected into interstellar space. And although it's a long time in the future, it would be nice to know which of those is likely to happen. We'd like to know why there are so few planets in the solar system. Why are there 8 planets rather than perhaps 20 or 50 or 2? And it's almost certain that the number of planets in the solar system and the configuration of planets in the solar system has been determined by long-term stability requirements for the system. We'd like to be able to calibrate the geological time scale over the last few tens of millions of years. One way to do this is that there are periodic variations in the Earth's temperature, which can be measured by the oxygen isotope ratio in, for example, seabed cores. It's likely that these, to some extent at least, that these periodicities are driven by periodic variations in the insolation received by the Earth due to variations in its orbit. If you can understand the Earth's orbit over the last few million years, then you can perhaps understand these oscillations and then use them to calibrate other markers of the geological timescale. You'd like to understand how dynamical systems behave over very long times. The solar system is a prototype of systems in which the motion is nearly integrable with small additional perturbations. And you'd like to know if you have very small perturbations acting over a very long time, do they cancel out or do they add up? One other system in which this question is relevant, of course, is the Large Hadron Collider. The number of circuits that protons typically make in the Large Hadron Collider is comparable to the number of orbits that planets make in the solar system. And in fact, there have been quite profitable interchanges between the solar system dynamics community and the designers of particle accelerators on how to model these effects. And of course, you'd like to understand the properties of extrasolar planetary systems. We now have thousands of extrasolar planets. And by understanding the behavior of the solar system over very long time scales, you can understand other planetary systems and perhaps constrain their properties. So you then ask, how do we solve the problem? Many famous mathematicians have tried to find analytic solutions or constraints on stability of the solar system, starting with Newton, and much more recently, including Kolmogorov, Arnold, and Moser. The difficulty with these attempts to find analytic explanations is that they always require either additional assumptions or sizes of the perturbations that are much smaller than you see in the actual solar system. And this was commented on very nicely by Poincaré, who pointed out that those who are interested in the progress of celestial mechanics must be astonished at seeing how many times the stability of the solar system has been demonstrated. It's demonstrated by Lagrange, it was demonstrated by Poisson, it was demonstrated after Poincaré by Kolmogorov, Arnold, and Moser. Were the old demonstrations insufficient or are the new ones unnecessary? And of course, the answer is that the new ones hopefully have fewer assumptions than the old ones, but still do involve some artificial assumptions. So I think it's clear that the only feasible approach is numerical computation of the planetary orbits. And most of what I'll focus on is what we've learned, how you carry this out, and what we've learned from these numerical integrations of the orbits. Let me first say a little about why these are hard. The natural tendency is to believe that Moore's law has made all computations easy to do. The difficulty with these is that most of the speed up we've seen in recent years has been from massive parallelization, and this is a classic example of a problem that's difficult to parallelize. Given time step requires calculating the gravitational interactions between all the planets, which requires of order n-1/2 operations, but n is pretty small, it's only 8, so you can't speed things up by massive parallelization in the sense that you do with, say, a cosmological n-body simulation. There are parallel in time algorithms which offer some promise for doing better, but at least in the solar system context, those have not really been explored and look reasonably difficult to implement. The second problem, apart from parallelization, is that you need sophisticated integration algorithms to avoid spurious numerical dissipation. And I'll digress for a moment or two to describe a toy example of why those are necessary. The toy example would involve following a test particle in the force field of a point mass. So I'll set G and the mass of the attracting body to unity. So the equations of motion are simply that the time derivative of the position is the velocity, the time derivative of the velocity is the force. The simplest integration algorithm is Euler's method, in which you just advance the position and then you advance the velocity. An alternative is the modified Euler, in which you advance the position and then advance the velocity using the force calculated at the new position. There's leapfrog, in which you advance the position over half a time step, then you advance the velocity using the force at this intermediate position, then advance the position again. And the final would be a standard fourth order Runge-Kutta method, the kind that you find in all the textbooks. And this is what you get for the growth of the error from the 4 different integrators for an orbit with an eccentricity of about 0.2 and the same number of force evaluations per time step. You can see that Euler's method is terrible. It has an error of order unity in just 100 orbits. The best of the methods at short time scales is the Runge-Kutta, and leapfrog in green is certainly better than modified Euler in blue. But you can also see that the remarkable feature of the modified Euler method and of the leapfrog method is that the upper envelope on the energy error is absolutely flat. There's no sign of any secular growth in the energy error. Runge-Kutta starts off better but has a linear growth in the energy error, which after a few hundred orbits means that its error is worse than in the other, in these two methods, even though it's a fourth order method instead of a first or second order method. And it's important to understand why this almost magical property of these two integration algorithms occurs. The answer is most easily seen by thinking of it as a problem in Hamiltonian mechanics. We're integrating in a Hamiltonian that has a kinetic energy part and a potential energy part in these equations of motion. And to create a numerical integrator with some time step, you can invoke operator splitting. That is, you advance the particle first under the kinetic energy part, which involves simply advancing the position at constant velocity, or you can advance it, then you advance it under the potential energy part, which gives you a kick in the a change in the velocity and no change in the position. And the combination of these two is simply modified Euler. The conclusion from this is that modified Euler is a Hamiltonian map or a symplectic map because it consists of the composition of two steps, each of which is derived from solving the equations of motion in a Hamiltonian, although in different Hamiltonians. And this is an example of the general principle of geometric integration algorithms. It's that a numerical integration algorithm that preserves some geometric property of the original set of equations, whether it's being symplectic, being time reversible, or something else. And the motivation for using these is that over very long time scales, preserving the phase space geometry of the flow that's present in the real dynamical system is more important than realizing the one-step error. The other way to say this is if you're trying to integrate an orbit, a circular orbit, Runge-Kutta tries to take you to a time step that's as close as possible to the actual position, whereas a symplectic method, roughly speaking, will take you to the closest position it can find that's on the circle. So Runge-Kutta will spiral in or spiral out, but a symplectic algorithm will not. So that's the basic reason why these two integrators, leapfrog and modified Euler, which are symplectic, work better over long periods than Runge-Kutta, which is not. If you then apply this general philosophy to integrating planetary systems, again, you split the Hamiltonian into a kinetic energy part and a potential energy part in the case of a planetary system. The potential energy part is the potential from the sun and all the other planets. And you could go ahead and use leapfrog to integrate this. However, a much better, you can split this Hamiltonian any way you like, as long as each of the parts is separately integrable. And a much better split is to split it, instead of into a kinetic energy part, into the Kepler Hamiltonian part, and then the rest of the potential due to the mutual planetary interactions. The reason this is better is that this Hamiltonian is smaller than this one by a order the ratio of the masses of the planets to the mass of the sun, which is 10 to the minus 3 to 10 to the minus 6. And that means that by making this split, you automatically reduce all of the integration errors by a factor of order the ratio of the planetary mass to the solar mass. So this part you can integrate because the Kepler problem is analytically integrable. This part you can integrate because it only depends on positions, so it just gives a kick in velocity. So all this integrator consists of is writing the position and velocity in orbital elements and advancing the orbital elements, then converting to position and velocity and giving a kick, then converting back to orbital elements and advancing the orbital elements and continuing to do this oscillation between orbital elements and Cartesian coordinates. For that reason, it's come to be called a mixed variable symplectic integrator. And using this with leapfrog has become the workhorse for almost all very long integrations of planetary systems. So that's roughly what you have to do to manage the truncation error in integrating a planetary system. You also have to manage round-off error because you're taking so many steps. Typically, the round-off error in an integration step will be a few bits. So if you have a standard double precision with 53 bits, the fractional error will be a few times 10 to the minus 16 per step. And the critical thing is how that small error accumulates. There are, roughly speaking, two possibilities. If you have systematic errors, you get an error of the same sign at every time step. So if you have, say, 20 steps per orbit times 10 to the 10th orbits, you'll accumulate a fractional error of about 1 part in 10 to the 5th. On the other hand, if you can arrange so that the error is random at each time step, that is half the time in one direction, half the time in the other direction, the total error will grow like a random walk, which will be the square root of the total number of time steps. And that gives you an error of around 10 to the minus 11 or 10 to the minus 10. So it's absolutely critical, as you can see, to avoid systematic round-off and only have random round-off. And random round-off is about as good as you can do. Eliminating systematic round-off is kind of like, you know, trying to get all the dust out of your house. It's very difficult. The first thing you have to do is use a machine that has optimal floating point arithmetic. That was defined in an IEEE standard in the 1980s, and fortunately is now satisfied reasonably well by most compilers. You also have to eliminate all fixed non-representable numbers. So for example, 1/3 is not represented exactly in any floating point, binary floating point format. And if you have a 1/3 anywhere in your integration algorithm, it will produce an error that always goes the same way at every time step and lead to systematic round-off error. The solution in the case of a number like 1/3 is, instead of multiplying by 1/3, you just divide by 3. Since you're dividing a different number each time by 3, the round-off will tend to have a random direction. And then you simply check that the error in the orbital elements in an integrable problem grow as the square root of the time rather than the time. And it really is true that when you've eliminated the last source of systematic round-off, all of a sudden your energy error your errors will drop by a factor of 10 to the 5th. So it's quite a dramatic change. Okay, so assuming that you have a set of integration techniques that can handle the problem, these are the equations of motion, just Newton's laws for the 8 planets in the sun, with a set of small corrections. The small corrections can include the satellites of the planets, general relativity, big asteroids. All of these are at levels less than a part per million, but they're completely straightforward to include. The uncertainties that you can't model well are small asteroids. There's contributions to the level of a part in 10 to the 10th from the accumulated effects of smaller asteroids, the effects of the Kuiper belt beyond Neptune. The sun is slowly losing mass. There's drag of the solar wind on the magnetospheres of the planets, tidal forces from the Milky Way, passing stars. It's unlikely that we've had a nearby encounter from a passing star, but it's something that you can't rule out. Errors in the planetary masses, errors in the initial conditions. All of these are at a level of less than a part in 10 to the 8th. And so to a very good approximation, the solar system really is an isolated dynamical system described by a known set of equations, known initial conditions. So it's the sort of thing that would have made Laplace very happy, and there's some hope that you really can do what he wanted, that is outline the future and the past completely. So when you do the integration, what you find is at the end of a few billion years, the orbits look almost the same. These are stroboscopic plots of what the orbits of the 4 inner planets look like a short time into the future and into the past, around 7 gigayears into the future and 4.5 gigayears into the past. And you can see that everything looks about the same. That is, there have been no dramatic major changes in the orbits of these or any of the other planets. Nevertheless, this exercise was not boring exercise because the system has exhibited very interesting behavior. In describing that behavior, let me just start by reminding you of the, crudely speaking, dynamical systems are of two kinds, regular systems and chaotic ones. Regular ones are predictable and well-behaved in the sense that if you make a small change in the initial condition, the changes in phase space grow linearly. So this includes, golf, the simple pendulum, every problem in a mechanics textbook, and planetary orbits on short time scales, because we know we can predict them well enough to send spacecraft to them. Chaotic systems are difficult to predict. They're difficult to predict because small differences grow exponentially at large times with an e-folding time called the Lyapunov time. Generically, they'll appear regular on timescales that are short compared to the Lyapunov time, so you'll get a linear growth on short timescales and then an exponential growth on large timescales. And these include, the weather, the double pendulum, billiards, and so forth. The remarkable discovery about the solar system is that when you integrate on long times, all of the planetary orbits are chaotic. The Lyapunov time is between 5 and 20 million years, which says that over the lifetime of the solar system, the orbits of the planets have undergone several hundred e-folds. So for example, this is a calculation of the evolution of the solar system where Jupiter, there are two calculations. Jupiter has been displaced slightly from one integration to the next, and this plots the difference in position between the two Jupiters over about 10% of the age of the solar system, and you can see an exponential growth with a Lyapunov, corresponding to the Lyapunov time of about 20 million years. Until, I guess, at very large times, the two Jupiters are on opposite sides of the solar system, and the separation saturates because the separation is about as far apart as they can get. You might ask whether this could be an artifact due to numerical errors or problems with the integrations. Of course, you can't be sure, but there's pretty convincing evidence that it's a real effect. This, for example, is a paper from Wayne Hayes a few years ago in which he integrated the system with the same parameters and the same initial conditions using a variety of different integration methods. Two of them were using the leapfrog and the mixed variable symplectic method I mentioned before with 2 time steps, 4 days and 8 days. One was a calculation using a 14th order non-symplectic multi-step method. And then one used an extended precision 80 bits with remarkably a 27th order integrator. Basically, you just expand the equations of motion in a Taylor series to 27th order, and then you can use a 220-day time step. This is the extended precision one. You can see that the differences are smaller because the contribution to seeding the differences from round-off error is smaller, but in all of the integrations you see a characteristic exponential growth with a Lyapunov time of around 10 million years. I should also point out that although these saturate here, when the two systems have their Jupiters on opposite sides of the solar system, the initial starting separation between the two Jupiters was 1 millimeter. So they really have undergone a dramatic exponential growth in the separation. Most of the chaos is in the orbital phases, not in the overall shapes and sizes of the orbits. That's why in the picture I showed you before, the orbits look more or less the same at short times and several billion years into the future and the past. But what it does mean technically is that when you came, for example, when you came to this lecture, the change in the tidal force on Jupiter from the motion of your body was sufficient to change the phase of Jupiter's orbit 5 billion years in the future by many radians. Okay, so what are the other implications? You can't make accurate predictions for the positions of the planets beyond about 1% of the age of the solar system, beyond a few tens of millions of years. Over longer times, you can only make statistical statements about the future of the solar system. You have to run many calculations with small changes in the initial conditions that span the range of uncertainties in the initial conditions. It says, so you can only make statistical statements about the stability of the solar system. It means the solar system is a bad example of a clockwork universe, so in the end, Laplace would be unhappy about the situation. It ironically turned, although this was the inspiration for Laplacian determinism, it's a very bad example. Although most of the changes in the chaos is in the phases of the planets, that's not true for Mercury. Mercury actually undergoes a random walk in the other orbital elements. And in about 1% of the integrations that have been done, the eccentricity of Mercury actually grows large enough that it undergoes a catastrophic event, which could be a collision with the sun or another planet or escape from the solar system. So this is an example of an ensemble of simulations run by Lascar and Gastineau. Mercury, in all of these simulations, each color represents a different integration. Mercury started off with its current eccentricity, and over 5 gigayears into the future, you can see that there's a wide range of eccentricities, but in a small fraction of the cases, the eccentricity gets high enough that Mercury can collide with Venus, occasionally even with the Earth, or collide with the Sun. It also turns out that the results are very sensitive to minor details of the configuration of the solar system. For example, if you do the same calculations over again, but you leave out the corrections for general relativity, the fraction of high eccentricity outcomes for Mercury increases from 1% to 60%. So you really have to include a lot of small effects to get things right. It also turns out that the statement that the solar system is chaotic is not entirely true. If you vary the initial conditions within the range of uncertainties, only about 70% of the trajectories are chaotic, not all of them. So this says that there's a 99% chance that the solar system is stable until the sun dies. That sounds pretty good, but of course it doesn't imply that the solar system was stable in the past. We could easily have lost a planet through instability in the past, and we simply wouldn't know about it at the present time. Of course, we have no direct evidence for this, but there's suggestive evidence. These are calculations in which you follow the evolution of all the planets plus a large number of test particles that have been sprinkled in circular orbits between the planets, and ask what happens to the test particles as a function of their initial semi-major axis from near the sun out to past Neptune. You can see that a fraction of about 15 or 20% impact the sun, a small number impact the other planets or get ejected into the Oort cloud, and about 80% are ejected into interstellar space. They only survive when you get out past around 42, 43 astronomical units. That's good because we know there are objects out there in the Kuiper belt. They also survive in this narrow band here. That's good because that's where the asteroid belt is, but everything else is ejected. And so it's likely that, so either this is a coincidence or else the current spacing of the planets has to some extent been determined by the requirement that it's the minimum spacing that allows everything to be stable. So everything I've said so far is, I think, reasonably well accepted and pretty straightforward. And in the last part of the talk, I'd like to go on to an extremely speculative set of calculations on a similar subject. As I've said, we know the orbits of planets in the solar system are chaotic. There have probably been collisions or ejections of planets in the past. We'd like to know if any aspects of this process can be described analytically or semi-analytically without actually going and integrating a whole bunch of orbits for 10 to the 10th years. So in a sense, this is a question of whether you can apply any sort of general principles from statistical mechanics to trying to understand the properties of the solar system. There are lots of bad examples of trying to explain properties of planetary orbits from first principles. We know Kepler's 3 laws were very successful, but he had a law before that, which was that the spacings of the planets was determined by the requirement that they should fit inside the 5 regular solids. This, of course, was complete nonsense, but we're charitable, and so I guess we remember him for the laws he had that did work. There's Bode's law from the 18th and 19th century about trying to argue that the spacing of the planets satisfied an arithmetic sequence. And there are lots of other bad examples, but there are reasons to try again. First, if we have a theory, we can test it using n-body integrations. And if we want to know whether the theory actually applies to planets, we now have a large statistical sample of multi-planet systems from Kepler. These are all the Kepler systems as of about a year ago. The little dots are one-planet systems, and there are multi-planet systems from 2 up to 7 planets. So there's now plenty of statistics of planetary systems that we can compare to. In order to say anything, we have to have some understanding of when systems are stable. We have no analytic criteria for the stability of systems containing more than 1 planet, but numerical integrations give us approximate criteria. These criteria are usually expressed in terms of the spacing of the planets compared to their Hill radius, which is basically the radius at which the planet exerts a strong influence on a passing test particle, and it's given by the semi-major axis of the planet times the cube root of its mass ratio to its host star. And the numerical simulations show that if you have a multi-planet system, it's typically stable if the separations of adjacent planets exceed some number of Hill radii. So the pericenter of the outer planet, semi-major axis times 1 minus its eccentricity, the difference of that with the apocenter of the inner planet, semi-major axis times 1 plus its eccentricity, has to be bigger than this dimensionless constant times the Hill radius. This is an example of how the dimensionless constant depends on the number of orbits you require stability for. There's a certain amount of variation, but roughly you need about 10 or 11 for this dimensionless constant if you want planets to survive for the lifetime of a typical planetary system. If you're going to apply general principles to planetary systems, you're plagued by the fact that in contrast to most systems you can use statistical mechanics on, planetary systems aren't homogeneous and they don't have a large n. The solution to that is to use a model called the sheared sheet. Essentially, the equation of motion for a planet is just the equation of motion at Kepler potential plus the additional potential due to the other planets. If I transform to a frame rotating at some angular speed appropriate for a circular orbit at some reference radius R0, I just add a centrifugal force and a Coriolis force. You then expand the radius or the position vector around this reference radius in Cartesian coordinates, keep only the first order terms, and you get a set of model equations which are valid when you have a lot of planets at small separations and small masses. And these equations are called Hill's equations or the sheared sheet equations. You can think of them as basically taking a small portion of the planetary system, putting a Cartesian box around it and expanding it. Because these equations have a transformational invariance, that is, they're invariance if you change the radial position and then add a shear in the azimuthal direction, you can simply superimpose boxes, Cartesian boxes of this kind that shear past each other with shearing boundary conditions, and end up with a system that is homogeneous on the large scale, and to which you can, because it's homogeneous on the large scale, you can put a large number of planets in it and apply standard methods from statistical mechanics. So all of that's, I think, relatively straightforward and innocuous. In order to say something about stability, I'm going to impose an ansatz, which says that planetary systems fill uniformly all the region of phase space that's allowed by stability. This is sort of like an ergodic model in statistical mechanics, but not really, because ergodic models are for closed boxes with reflecting boundary conditions. Here, because it's a stability constraint, the boundary conditions are absorbing. Once you reach the unstable region, you disappear. Nevertheless, if you'll allow me to make that assumption, you can write down the partition function or the joint probability distribution trivially. It's just the product of the phase space volumes, which you can work out from Hamiltonian mechanics is the range of semi-major axis times the range in the square of the eccentricity, and then a step function which is 0 if the ratio between the pericenter of the outer orbit and the apocenter of the inner orbit is less than this dimensionless number times the Hill radius. This is quite similar to one of the classic problems of exactly soluble models of statistical mechanics, the one-dimensional gas of hard rods instead of hard spheres, that has a partition function that just says the probability distribution is uniform apart from the excluded volume that says that adjacent particles have to be separated by more than the length of a rod. So once you have this, you can, for example, work out what the eccentricity distribution should be. You just integrate over all of the eccentricities except one and all of the semi-major axes. And when you do that, you get a form for the eccentricity distribution that's an exponential times a prefactor proportional to the eccentricity with a free parameter that's kind of analogous to a temperature. You can then compare that to numerical simulations of late stages of planet formation in which particles are allowed to collide and merge together. And you get a comparison that looks like this. The agreement is actually remarkably good with one free parameter representing this kind of temperature of the system. You can also work out what the distribution of semi-major axis differences between nearest neighbors should be. This is also analytical, though a little more complicated. Comparing to the same simulation, I've written this in terms of the semi-major axis difference minus the forbidden region because of stability, so that in these coordinates, the unstable region over here should have no planets in it. You can see that's pretty accurately satisfied, and the predicted curve fits the distribution of semi-major axis differences pretty well. And this is being done with no free parameters because I'm using the same value for this parameter that I did before. So I think that suggests that this simple model has captured a significant fraction of the real physics that's going on in the simulations at least. The next question would be whether it captures what's going on in the real planets discovered by Kepler. This is the same plot, differences in semi-major axes. For a sample of Kepler planets, the difficulty here is that Kepler only measures planetary radii. It doesn't measure masses. So you have to convert to masses using a mass-radius relation that's been calibrated with only a handful of planets. And you can see the difficulty is that in the simulation, there's nothing in the unstable region less than 0 in this coordinate, whereas here there's a significant number of planets. Almost certainly the reason that these appear to be unstable is that there's really scatter in the mass-radius relation. You can this paper estimates what the scatter is, so you can just take the theoretical distribution and convolve it with the observed scatter. And when you do that, you get a predictive best fit curve that looks like this, which again I think is a pretty reasonable fit. It doesn't fit out here, but this tail at large separation is something you'd expect because Kepler doesn't find all of the planets. There are always planets below its detection limit. If you're missing a planet, you're likely to conclude that the separation to the nearest neighbor is much larger than it actually is. And so you expect to see some tail like this. With this value of the effective temperatures, you can predict what the eccentricities of the planets should be. Eccentricities are much harder to measure. This predicts a mean eccentricity of about 6%. The actual numbers vary. Typically, they're somewhat lower than that, but not always, and we'll have to wait to get better estimates of the eccentricity from Kepler to see if this prediction is coming out okay or not. The model also predicts that there's no equipartition, that is, that there's no correlation between mass and eccentricity. This is a plot not from Kepler, but from planets discovered by radial velocity, so it's a little misleading to look at, but you can see that the typical eccentricity is at best a weak function of the mass of the planet. So this prediction of the lack of correlation between mass and eccentricity, I think is reasonably okay. Okay, so that was my speculation. Let me finish by summarizing both the non-speculative and the speculative part. So what we're pretty confident of is that all of the planetary orbits in the solar system are chaotic. They have Lyapunov times short enough that they've undergone hundreds of E-folds in the lifetime of the solar system. That for most planets, most of the chaotic behavior is in the phases of the planets, so the shapes of the orbits are staying the same. That means they're not going to collide or do anything drastic. But the eccentricity of Mercury's orbit is undergoing a random walk, and there's a small but non-zero chance that it will be destroyed in the lifetime of the sun. The results are very sensitive to details, the addition or removal of relativistic effects, small changes in the initial conditions, and so forth. It's likely that although we're stable in the future, that ejections or collisions of planets have happened in the past, and that's part of how solar systems evolve. And if you have that model for how solar system evolves, you can make natural and simple models of the distribution of planets in phase space that seem to capture a lot of the statistical properties of the many orbits that have been discovered in extrasolar planetary systems. Okay, I'll stop there. Thank you.
Scott, for this intense lecture. Any questions?
You haven't said anything about tides.
Yes. The reason is that in the current configuration of the solar system, tides are, of course, important for satellites. They're important for changing the spins of some of the of Mercury and perhaps Venus, but there hasn't been any significant tidal evolution in the orbits of any of the planets in the solar system.
I was thinking about the exoplanet, actually.
Yes, so in the case of the exoplanets, some of the Kepler planets that are sufficiently close to their host star have certainly evolved by tides. In doing our comparisons, we eliminated planets that were closer than, had periods smaller than 10 days, which I think gets rid of most of the effects of the tides.
And even between planets, some of these, if you look at the period ratios of compact system in the Kepler catalog, you find that they are located close to resonance, but not quite, and these things which generally people attribute
So there is certainly some evidence of features in the distribution of Kepler period ratios near some of the low order mean motion resonances. It's likely that those features, well, those features could be caused by migration, or they could be caused by dissipation in the protoplanetary gas disk. I think the striking feature about them is not so much that they're there, but that they're not stronger. In standard models of planet formation, if the properties of the planet are determined by, if its orbital properties are determined by migration from much larger distances, you would normally expect that most of the planets should be exactly in low order mean motion resonances. That's not what we found, and that was one of the surprises from Kepler. So, it's a question of whether you think the cup is half empty or half full. I think that the lack of strong features at resonances tells you that most of the planets formed in their late stages by some sort of process like the kind I'm trying to model, involving eccentricity excitation and collisions, rather than by just migrating.
What about giant impacts, since you think that the moon may be formed from a giant impact? What are the implications?
Well, so I think that in the natural model for formation of terrestrial planets, there's a stage at which there are embryos, small Mars-sized bodies, and then those, as you say, collide and grow by giant impacts. That's, in a certain sense, what I've been trying. So I think that's a plausible stage of formation that can be modeled to some extent by this kind of uniform distribution in the stable regions of phase space. Ideally, what you would like is to use simple arguments like that to determine both the orbital elements and the masses that arise from the giant impacts. I'm not aware of any good statistical model that can reproduce the mass distribution you get from this phase of giant impacts. So all I was trying to do was model the distribution of eccentricities and separations. So I think the kind of impact that formed the moon is the kind of thing that I think can give rise to this kind of statistics.
Is there another question? Go ahead.
Would the planet 9 have an effect on the long-term stability if there was such a...
Well, I can give another lecture on Planet 9, but first of all, I think it's probably not worth speculating too much about Planet 9. But with the parameters that they have proposed for this Planet 9, it never comes close enough to the planetary system to have any significant effect. Now, having said that, of course, because I also said that the stability is quite sensitive to small changes in the parameters. So maybe it could, shift things a little bit in or out of a chaotic zone, but its direct effect, I think, is almost certainly negligible.
Is there another question? If not, I would like to invite you. There's supposed to be an afro outside. I just came back from the conference in Davos, so my secretary was supposed to take care of it. If there's no afro, don't blame me too hard. But the purpose of the afro is so that you have a chance to interact with Scott, ask him more questions and so on, and in a more relaxed setting. And I hope you come back at 4 because Scott will tell us about supermassive black holes. Thank you, Scott.
Thank you.